Hello, this is John Messick in Geographic Information Systems. Chapter 2, Coordinate Systems. In this recording, I preview this chapter and offer some study suggestions. Let's begin by identifying objectives when you read and study this chapter. You need to define a geographic coordinate system and explain how latitude and longitude are organized and used to locate specific places. Define a map datum, especially in the context of how datums are used in GIS. Define a map projection and explain the basis for the two criteria that are used to classify projections. Describe the organization of the Universal Transverse Mercator Projected Coordinate System, better known as the UTM system. Similarly, describe the organization of the State Plane Coordinate System, or SPC. Describe the organization of the Public Land Survey System, PLSS. Explain the purpose of a projection definition file in ArcGIS. Distinguish between defining a projection or a coordinate system and reprojecting in ArcGIS, fundamentally different operations. Finally, define on-the-fly projection in ArcGIS. I've expanded certain of these objectives. Let's look at the first one. This had to do, of course, with latitude and longitude. A geographic coordinate system defines locations on the globe, and it uses longitude and latitude. We'll look at figure 2.2 momentarily. Lines of longitude, also known as meridians, extend between the poles, and the numbering of these begins with the meridian that passes through Greenwich, England, designated 0 degrees. Those meridians are designated east and west of the starting point, and of course reach a maximum of 180 degrees. Lines of latitude, also known as parallels, encircle the Earth. They start at the equator at 0 and extend north and south of the equator to 90 degrees. When we identify a location on a geographic coordinate system, we typically use longitude and latitude, expressed in degrees, minutes, and seconds, or sometimes decimal degrees. For example, Joplin, Missouri has the geographic coordinates in degrees, minutes, and seconds, or DMS, of 37 degrees, 4 minutes, 40 seconds north, and 94 degrees, 30 minutes, 40 seconds west, that would be the longitude, and expressed in decimal degrees, that would be 37 point, and you see the fraction there, and minus 94.5, you see the rest of the fraction there. Again, those are decimal degrees. You do need to understand how to convert from DMS, degrees, minutes, and seconds, to decimal degrees. Here's how to do that. You take the seconds, divide that by 60, add that result to the minutes, and then divide that result by 60, and finally add your calculation to the degrees value. So if we take 37 degrees, 4 minutes, 40 seconds, we start by dividing the 40 by 60, add that to the 4 minutes, and then divide that result by 60, and finally add the value to 37. So you end up with that 37.077778. As a side note, in GIS, the directional indicators for latitude using north or south and east or west for longitude are often omitted, and instead negative values for longitude are used when we're describing locations in the western hemisphere, or for latitude in the southern hemisphere. Here's figure 2.2 that shows lines of longitude and latitude, and a couple of locations have been identified there. I've expanded Objective 4, having to do with the Universal Transverse Mercator coordinate system. This is a widely used projected coordinate system, and it divides longitude into zones. There are 60 of those. They're numbered. Each of those zones is 6 degrees wide, and they extend 84 degrees north and 84 degrees south of the equator. So the polar areas are not included in the UTM system. There is an alternative system for those polar regions. For example, Missouri is in UTM zone 15 north. Idaho is divided between zones 11 and 12. We'll see figure 2.2 here momentarily. When working in the northern hemisphere, locations are given as an X and Y coordinate system in meters. The units of measure are typically meters. The X is often referred to as the easting value, the Y as the northing value. The numbering within each zone for these X and Y coordinates begins at a false easting that is 500,000 meters west of the middle of the zone, which is also referred to as the central meridian for a given UTM zone. The result is a system that is accurate within 1 meter. Many newer USGS, United States Geological Survey, topographic maps show the UTM grid superimposed, and that grid is typically 1,000 meters in size. The grid lines are 1,000 meters apart. I do have a separate handout on this, and there is also a narrated screen recording describing how to locate specific points in the UTM system. This is figure 2.12 showing the UTM zones for the United States. Notice Missouri in 15 north. Also notice that Idaho is divided between 11 north and 12 north. Idaho actually has developed its own special coordinate system that is somewhat of a hybrid of the UTM system. So we will explore that at least briefly in the assignment for this chapter. I also want to say a little more about Objective 5 having to do with the State Plane Coordinate System, or SPC. This was originally developed for land survey in the mountain states, but my impression is that many cities and other local units use the State Plane Coordinate System. The state plane zones are shown in figure 2.14, and locations are very often in feet, since here in the United States we tend to be non-metric in governmental agencies, but they can be also in meters. So here are UTM zones, a map of the United States showing the counties. Those are the little small grids in most cases, and then you see the heavier black lines that represent the state plane coordinate system zone. So Missouri, you see, has 3 that are arranged vertically. Kansas, on the other hand, has 2 zones that are north and south of each other. I also have expanded Objective 6 having to do with the public land survey system. This actually is not a projected coordinate system, but more a land partitioning system. This is used in cadastral, legal descriptions, and other purposes. That word cadastral has to do with ownership, basically. Locations are defined in the PLSS system using township sections and subdivisions of sections, and we will explore that in a separate handout. There is also a narrated screen recording that describes how to identify specific locations using township and range line and so on. Figure 2.15 describes the organization of the public land survey system. In the illustration on the left, you have a baseline and a Boise meridian. This is obviously an example from Idaho. That meridian would typically be referred to as a range line. If you are familiar with Joplin, you know Range Line Road, that is one such line in the public land survey system. Notice the east-west lines are numbered T1S, T2S, T1 North, and so on. Those are township lines north and south of the baselines. And then similarly, the range lines are numbered west and east of that main range line or meridian. Those squares describe a township, which is further subdivided into 36 sections measuring 1 mile by 1 mile. We can subdivide a section into quarters, and each quarter into smaller units, and so on. I have a narrated screen recording that describes that process in more detail and also explains how to describe a specific location using the public land survey system. The last three objectives in this chapter, 7, 8, and 9, are associated with the use of coordinate systems in ArcGIS. We have 2 assignments that relate to this, and after completing those assignments, I think you'll develop a better understanding of how projections result in various kinds of distortion. We'll certainly learn about the projection definition file, and we will, in our assignment, define projections and reproject. There's a fundamental difference in those processes. And we will develop a good appreciation for the way ArcGIS uses on-the-fly projection. There is a table in your book that describes the organization of coordinate systems in ArcGIS, Table 2.1. If we look at this, we have predefined coordinate systems that may be geographic or may be projected, and you see a couple of examples there. It is also possible to develop your own custom projection, and in fact in Idaho that has been done. There is a specialized transverse Mercator projection system used widely in Idaho, the IDTM. Let me end this preview with a couple of questions. What are some of the major issues or problems created by differing projections in GIS? And how does our GIS software help to minimize those issues? Your text has some illustrations and explanations of problems with projections, and then I think after completing the assignments you will appreciate how ArcGIS helps you manage coordinate systems. I'd like for you to visit a couple of geospatial download sites, probably for states, like the Missouri Spatial Data Information Service and others that I've cited earlier in the course. And I'd like for you to look at the projection and data information that is available in those downloadable files. Is there one projection or one coordinate system that is used for those source files, or are there multiple choices? The same thing for datums. I think you'll find in many cases there is some variety, and that will make you more appreciative of how ArcGIS is able to minimize problems with different projections. That completes this presentation. Thanks for watching.